gain. The second condition is the field should properly connect it to the armature. Field and armature should have proper connection in order to aid the residual flux. And the next third and fourth we can give to critical resistance and the critical speed of the generator. And the best condition for a shunt generator to build up voltage is to be on no load. In spite of this, still the voltage is not getting built up. When you start the generator means it may be due to improper brush contact. Now, let us consider you are given a shunt generator which is building the voltage normally. If it doesn't build up, what you will do, for example, you will check for the first condition, because the first preference you have to go to 5 ohm. So you will do automatically field flashing. So it's a simple process. You can apply a DC voltage for 10 to 15 minutes in a zero. So after doing this, when you start the machine, the build up of voltage will take place. Even though there is 5R, then also the build up of voltage is not taking place means definitely the field is not properly connected to the armature. Then you will reverse the field winding because the residual flux got erased away, do the field flashing, again reverse the field winding, connect it, you start the machine. So these two are empirically or by trial and error based method. By seeing the machine, you can simply judge and you can automatically rectify them. But what is RC, what is NC? That is what the discussion. Keep the heading. Determination of critical resistance and critical speed. I think this fan is not working. Determination of critical resistance and critical speed. Now listen. In order to determine critical resistance and critical speed of a self-excited shunt generator, you require to plot open circuit characteristics or no load saturation characteristics or magnetization characteristics. All are same. These are basically no load induced EMF versus field current. If you see the EMF equation or in the generator, you have written Eg as the induced EMF. If you remember this Eg, when you connect some load, let it be Eg. If there is no load across the armature, no load means armature is just open. So let the voltage in the armature be E0. What is the difference between E0 and Eg? You will understand after the discussion of armature reaction. So the no load induced EMF versus field current. You want to plot this particular characteristic in order to determine critical resistance and critical speed of the given generator. Now, what is critical resistance means? It is the maximum resistance of the field winding above which the generator won't excite. Field resistance has a value. Yesterday I have discussed already. Field resistance value is around 50 to 250 ohms. This is the original resistance of the field winding. RC is theoretical value, some imaginary value. It is not natural value. This is original value of the field winding. It's over. RC is not this. RC is a value. Theoretically, it is the maximum value, a critical limit. If the resistance of the field winding is above that, the machine won't excite. First, write out the definition of critical resistance. It is the maximum resistance of the field winding. It is the maximum resistance of the field winding above which the generator doesn't build up voltage. The generator doesn't build up voltage. Write down the definition for critical speed. Critical speed. It is the minimum speed. It is the minimum speed of a generator below which voltage doesn't build up. Below which voltage doesn't build up. You underline above in the above definition for critical resistance, underline below. Just to make you understand the concept. While you plot a curve and you will calculate RC and C, you just think about above and below these things. Right, to determine these parameters, open circuit characteristics or no load saturation or magnetization characteristics in bracket you keep this E0 versus IF. E0 versus IF is required. Carefully observe one thing. If you want to plot E0 versus IF, means let us say IF is 1 ampere. Take a simple generator where the maximum IF value is 1 ampere rating. So E0 in this axis volts. You require IF 0, IF 0.1, IF 0.2, 0.3, 0.4, 0.5 like that. Different values. For different field current values, what is the amount of voltage? This is what the current is telling you. But this is impossible for a self-excited shunt generator to plot. You cannot plot this particular characteristics for a self-excited shunt generator. Why? Because take a self-excited shunt generator. This shunt generator, let us say all the conditions are successful. All the above 5 conditions, first 5 conditions are successful. Now you started the machine. Once you start the machine, let us say between 0 and 5 seconds. Within these 5 seconds, as the motor rotates, it reaches rated speed. Automatically, phi r cutting the conductors. Current is coming into picture. Current is going into the field winding, and it produces MMF that will add phi r, more voltage, more current, more flux, more voltage, more current, more flux, cumulative build up. Finally, the poles gets saturated. Once the poles get saturated, even though the current increases, flux won't increase. Once flux won't increase, automatically voltage won't increase. It becomes a constant value. That thing happens within 0 to 5 seconds. So let us consider with respect to time. Once when IF is 0, let there be small residual flux. Due to small residual flux, a small voltage. After that, this small voltage, ER, produces what? IR. So this ER produces some IR. IR means nothing but flowing into the field winding. So this is field current only. So that flows into the field winding. So this IR produces more flux because IR is flowing into the field winding. IR produces flux. So this flux is added with this and produces more voltage. So you will get more voltage for this. So this more voltage will produce more current again. So current will increase. So this current again produces more voltage. So like that, this current is increasing within how much time? Maximum 5 seconds or 10 seconds. So when you start a shunt generator, within 10 seconds, the voltage build-up takes place and gets saturated, readily available. Now you want this characteristic. How you can do it? Think about that. Now you want this characteristic. Within 10 seconds, you can do nothing to the machine. You start it, readily generator is available. Now what you require? You require different IFs. What is the voltage? How to do this? The only option is you have to separately excite the shunt generator. The only option is you have to separately excite the shunt generator. How to get different field current values? Within 5 seconds, IF becomes 1 ampere, rated value, finished. This becomes rated value and you are getting some E0, exactly some rated value, finished. Within 5 to 10 seconds, everything is stabilized. Now, if you want to vary field current from 0 to 1 ampere, one option is generally as you think, you can connect some resistance in series with the field winding and you can vary. But you can't expect that to do in this particular thing. Why? Because you want to calculate the resistance of the field winding. You want to calculate the resistance of the field, that is critical resistance of the field winding. Yes or no? You want to calculate the critical resistance of field winding. If you insert some external resistance in series with the field winding, RC value gets manipulated. Is the point clear? Original RSH value will not be there on the machine if you connect some critical, some resistance. One more danger is there, that is, what is critical resistance? It is the resistance above which means if you insert some resistance, there is a chance of resistance in the field winding increasing above critical. Then what happens? No build-up of voltage. So don't think of that particular condition, inserting some resistance in series and by varying the resistance you can vary the field current. That particular chance is not there in this particular method because you are manipulating the resistance of the field winding. You can't do that. So the next only option is you have to separately excite shunt generator. Better note. In order to plot these characteristics, self-excited generator, self-excited shunt generator is separately excited. You know what is separate excitation? The field circuit is independent of the armature. Across the field, there is an independent voltage source. So, when you vary the voltage source from 0 to maximum value, automatically the current in the field winding will vary from 0 to maximum. You can go within finite steps, required discrete steps. For each reading, what is the voltage across the armature, you can measure with the voltmeter and you can plot OCC. You cannot plot OCC for a self-excited shunt generator without making it separately excited. Remember that. So let us consider this is the shunt generator we want to calculate RC and NC. Now this is the armature winding, this is the field winding, both are run in parallel. So now isolate them. This is the armature of the generator. You know, a generator cannot work without a prime mover. Generator doesn't generate anything by itself. It requires. What is a motor? How to start it? Everything we'll discuss later. Just let us say this is a motor, a DC motor, coupled to a generator. If you find the generator, definitely it is coupled to a motor. Definitely. So let us take this generator armature coupled to a motor. Now, this motor is given a DC supply. Let us think this motor is started with its necessary starting steps, and finally this is running at rated speed. You want the characteristic between E0 versus IF. If current in the field winding increases, what is increasing? Flux is increasing. If current in the field winding is increasing, flux is increasing proportionally up to saturation. After saturation, flux won't increase. Now, as IF and phi both are proportional to each other, you are plotting E0 versus phi. Can we say that? You are plotting E0 versus phi. As you are increasing the current, flux is increasing. You are producing magnetization in the machine. This is nothing but magnetization. So that's why it is known as magnetization curve. And in this curve, you will observe the saturation point. That's why it is also called no load saturation. Why it is called as OCC, open circuit characteristics, means the generator is left open, no load. That's why it is known as open circuit characteristic. Now, you know E is proportional to phi into N. E is proportional to phi N. Means the induced EMF depends on flux as well as speed. You want a strict relation between E0 and the phi. If speed varies, will you get that relation? No. Speed should be maintained constant. If speed is maintained constant, only you can know the relation between E0 and phi. That's why OCC should be always plotted at a particular speed, at a constant speed. Now, this is the armature, this is the field winding. Physically, field winding is the armature stator only, on the stator only. On the armature, there is a stator, but you are making it separately excited. So, let us say the same DC supply. So using a potential divider, we can have variable DC voltages across the field winding. Now listen. So this is basically self-excited shunt generator, and you are intentionally making it separately excited. In order to get different field currents, you can vary with your hand using a potential divider. If this point is here, the voltage across the field winding is 0. As you move this point upwards, automatically the voltage will appear across the field winding. As the voltage increases in the field winding, automatically current also increases proportionally. Ohm's law. You can expect, you are applying DC, expect the same thing. You are applying DC voltage. So you think the circuit like this. There is some resistance here. What is this resistance? Original field winding resistance, 50 or 100 or 250 ohms, like that. So original field winding resistance is there here. When you apply some voltage across the resistance, what happens? Automatically the current will increase. If you plot a curve between V and I, how will you get? If you plot a curve between V and I, what will you get? A straight line passing through origin. Can you say that? So the slope of that will give you the resistance value. Can you say that? So this is field winding resistance RSH. So what is VF by IF? What is VF by IF? RSH, original resistance of the field winding. Now, test is very simple. You have to apply slowly from 0 to maximum rated values of voltage as well as the current, slowly. So first start the motor, run the motor at the rated speed of the generator. Let it be rated speed which is maintained constant. Then let us make V0 I0. Let us make V0 I also 0. No field winding. Let us imagine like this. Then when the generator is running at its rated speed, will the voltmeter deflect to any value? It will deflect if it has residual flux. It will deflect if the poles have residual flux. This is the field winding on the pole. Pole is magnetized already, field flashing. So under the pole, what is the small residual flux? So the armature conductors will cut the residual flux, and automatically what is produced? Small voltage. So if VF is 0, IF is 0, E0 will be around 6 to 8 volts. So OCC, if there is residual flux, never starts from origin. It will start with some small residual voltage value. And so on, like that. If you are increasing the voltage to 20 to 40 to 60, so on, automatically the current is increasing from 0.1, 0.2, so on up to 1 ampere. So this is the rated value. If you make VFS 220 is the rated value you are making. So E0 also increases so on to its rated value. First it will increase linearly. After that it becomes saturated. Means even though the current increases in the field winding, flux won't increase, then voltage won't increase. So now if you plot a graph between different values of IF, different values of E0, you have to record the, for each reading, for each voltage current value, what is E0, keeping speed constant. For each voltage current value, what is E0? Like take some 10 or 12 readings, sufficient readings. So when IF is 0, first one, OCC starts from some value, residual voltage 6 or 8 volts. After that, it will linear, and after that slowly it will get saturated. This is actually known as knee point. OCC represents vehicle. Any machine, the core is designed to operate for a particular flux density value. So generally, the preferred operating region is this knee point region. After this knee point, OCC gets saturated. This is before saturation, this is after saturation. Now, the next one is OCC is E0 versus IF. Now, you require one more thing, that is field resistance line. If you plot a graph between VF and IF, how it will be? Straight line passing through origin. This is shunt field resistance line. This is shunt field resistance line. It will cut OCC at a point P. So this is what is required to calculate RC/MC. From this, how to calculate the critical resistance? It means, according to the definition, it is the resistance of the field winding above which the machine doesn't build up voltage. Now, the shunt field resistance line will cut OCC at a point P, this point. So the significance of point P is the intersection point P is, if you extend this onto this axis, you are getting some voltage, right? E0. This is the maximum voltage the shunt generator can build up. Let us say this is O, this is Q. Length of OQ in volts is the maximum voltage the shunt generator can build up. Make a note like this. The intersection of field resistance line, with OCC, the intersection of field resistance line with OCC in bracket point P conveys the maximum voltage shunt generator can build up. Maximum voltage shunt generator can build up. So listen. This line you have plotted VF versus IF. In exam sometimes you won't be given VF IF characteristics. You will be simply given the shunt field resistance value is 100 ohms. But you will not be given VF IF all the data. You will be given IF and E0 only. To plot OCC you will be given 4 or 5 points. You can plot OCC and do everything. But you will not be given shunt field resistance characteristics, VF versus IF. You will be just given, let the shunt field resistance be 100 ohms or 50 ohms or 200 ohms. If you know this 100 ohms, you can easily plot that line. 100 ohms means it is nothing but VF by IF. You can make VF 100, IF as 1 ampere. Yes or no? You can take, if VF is 100, IF is 1 ampere. You know 50 by 1 is equal to 100 by 2 is equal to 200 by 4, like that. It's a linear curve. Like that, if you know 1 point 100 and 1, automatically you can plot from origin, you can plot a line. So you can go for 100 amperes here, some 100 volts here, and automatically 1 ampere, you can make a point. And this point is joined from the origin. So let us think this RSH value is 100 ohms. Let us assume this is 1 ampere, this is 100 volts. So you got a point like that, you will plot a line like this. That is the field resistance line for 100 ohms. Now 100 ohms is original resistance. This is original resistance of the field winding. In the given machine, this is the resistance. Now imagine, theoretically imagine, the resistance of the field winding is increased to 150. What will be the field resistance line? If the resistance of the field winding, let us imagine, is increased to 150 ohms, will it go up, will it come down? Definitely it will go up, right? 150 means definitely 150 by 1. 150 by 1 means same 1 point, the point you will get at 150. So you have to join, let this be 150. So you have to join one more line, 150, right? So what is this now? This is also shunt field resistance line for RSH value 150 ohms. Where is point P now? Is it the same value? Is it reduced or is it decreased? It is reduced. The maximum limit, the maximum capability or voltage the machine can build up has been decreased to some value, right? Now let us say the field resistance is increased to 200 ohms. Imagine the field resistance increased to 200 ohms. So definitely the line will go up. So let us say this point now. This is 1, this is 200. Then again, what happened to point P? Further decreased. This is the point P now. When the field resistance is 200 ohms. Let us say some X ohms, we don't know that. For that particular field resistance, the field resistance line is exactly tangent to OCC. Imagine the field resistance is further increased in such a way that for that resistance value, the field resistance line is exactly tangent to OCC. Let that resistance be RC. So you will get point P somewhere here in this region. So this is the maximum voltage the machine can build up. Now imagine the field resistance is increased beyond RC. The field resistance is increased above RC value. How will the line come? Is this the line or not? Where is point P now? In the residual flux region. The point P is only minimum limit 6 to 8 volts. So the maximum voltage the machine can build up is only, if you say this is the maximum limit the machine can build up, this is the maximum limit the machine can build up for this resistance, this is the maximum limit the machine can build up for this resistance, this is the maximum limit the machine can build up for this value of resistance, this is the maximum limit the machine can build up for above resistance value, above critical. What is this value? Residual voltage 6 to 8 volts. So what we say now, the machine won't build up. That's the maximum voltage. That's the maximum voltage means not beyond that. Maximum is only 1. So 6 to 8 is always maximum, means the machine won't build up any voltage. Right now. Plot a tangent to OCC. So this is normal. You will plot OCC, you will plot shunt field resistance line. These two are normally you will be doing first. Next, you have to plot a tangent to OCC, which is nothing but critical field resistance line. Can you say that? This is one field resistance line. If you draw one more, this is one field resistance line which is increased. This is one more field resistance line for the field resistance which is critical. So draw tangent to OCC. Let it meet at point R. Right now. Let it meet at point R. Drop a perpendicular. Drop a perpendicular to meet at T. Now listen. This is the field resistance line. If you have a point here, listen, if you have a point here, if you want the resistance value, you take what is the voltage here across this, you take what is the current. V by I gives you the resistance value, yes or no? Similarly, you have a point here, you want the resistance value of this line. Now what you will say, you will extend like this, RT, length of RT in volts, length of RT in volts by length of OT in amperes. V by I. What is this? Critical resistance. If you say RSH is 100 ohms, definitely this V is 100, this will be I is 1 ampere. 100 by 1 is resistance of this line. You want the resistance of this line, which is representing critical resistance of the machine. If you want the resistance of this line, you make a point on that. You extend that to this point, you will get some voltage value here. We don't know what is the voltage. Let it be RT, length of RT in volts, some X value. Similarly, you know OT, length of OT in amperes. So if you make V by I, you will get the resistance of this line, which is nothing but critical field resistance. So, according to definition, it is the resistance of the field winding above which the machine won't excite. So don't consider if the resistance of the field winding is above critical resistance, voltage is becoming zero. Voltage is not becoming zero, but the voltage becomes a lowest minimum value, some value minimum. That value is residual voltage. Remember that. When solving objective questions, you will get, if you see zero in option, don't see that zero for this critical resistance, critical speed, because machine won't build up voltage. That means the voltage across the armature is not zero, but some small value. Now, critical speed. According to the definition, it is the minimum speed below which. Now let us consider this OCC is plotted for 1500 RPM. Let us consider, assume like that. This OCC is plotted for 1500 RPM. If you are asked in exam to plot OCC for 1000 RPM or 1200 RPM and to calculate anything, data is given for 1500. So what you can do is, you know the simple relation Eg2 by Eg1 is equal to N2 by N1. So you have values like this, IF, E0 for 1500 you have. For example, let us say like this, IF 0.1 E0 10, IF 0.2 E0 20, IF 0.3 E0 30. Let us say like this, three values. Just you have this data with you. Now you plotted OCC for 1500 RPM between IF and E0. You are asked to plot OCC for 1500 other than 1500. Then for the same field current, flux is constant. Use this relation. Same field current, if the speed increases to 2000, let it be. Speed increases to 2000, for example, then this is N1 is 1500, N2 is 2000. E1 is 10. What is E2? Is the point clear? So calculate like that. So you will have E2 means Eg2 is equal to N2 by N1 into Eg1. So N2 is 2000, N1 is 1500. Multiply this with 10, multiply this with 20, multiply this with 30. You will get new values. Definitely more than 10, more than 20, more than 30, right? So you plot OCC for that. Will the curve come above or below? The curve comes above it, definitely. So as the speed increases, the curve goes up. Now let us consider the same procedure. You are proceeding for 1200 RPM. What happens? In the numerator you will have 1200, in the denominator you will have 1500. This factor is less than 1. So if you multiply with this, definitely it will be less than the previous value. So you will get OCC below this particular 1500. Now we zoom. OCC is plotted for 1200 RPM. Forget about all these critical resistances, all these things. This is over already. Now, just take again OCC, original field resistance line. Only see these two. This is original OCC at 1500. This is original field resistance line. Both are meeting at a point known as P, that is the maximum capability of the machine to build up voltage, maximum level. Then, if you reduce the speed of the generator and if you plot OCC, then definitely this residual flux, this small value will vary within small voltage. So small value, even though you can't recognize let us say this is OCC. If this is for 1500 RPM, let this OCC be for 1200. Where is point P now? Where is point P? This one, right? So what happened to the maximum value of the machine? Decreased. As the speed decreases, automatically it has been decreased. Now let us consider OCC is plotted for 1000 RPM. Where is point P? Further decreased. Further decreased. Now let us say some speed which is critical value, which makes, what is this blue line? What is this line? Original shunt field resistance line. Yes or no? This is original shunt field resistance line. Now, let us say, we don't know the speed, let us say NC, which is making the original shunt field resistance line is making tangent to OCC at NC, let us say. Now, at somewhere here you will have a point. Don't worry about this line because they are proportionally linearly varying. The length between this and this are linearly varying. If you take this point or this point or this point, it will be the same value because it is linear. So, you know, this is cutting OCC here, you make it a point here. Carefully observe. What is this point? This point is on shunt field resistance line. Yes or no? This point is on shunt field resistance line. Previously, there is a shunt field resistance line here. This NC, OCC at NC is making a tangent. Now, if you drop a perpendicular exactly, if you say this is R, once refer the diagram, if this is R, let us say this is S, let this is T. Length of RT representing 1500 rated speed. Length of RT representing 1500. Length of ST representing what? Critical speed. I'm repeating again. Length of RT, this one, length of RT is representing 1500 original rated speed, given speed. Now, length of ST is representing NC. Just put it like an equation here, mathematically. Length of RT represents rated speed or given speed N. Length of ST represents NC. From this, mathematically, you can write like this. RT by ST is equal to N by NC. All are proportional. So no need of volts or amperes. Length of RT you can take in centimeters. Volts or amperes, anyway they will cancel out. So from this NC is equal to ST by RT into N. N is known value. It may be rated value or given value. N is known value. So if you observe, according to the definition of critical speed, it is the minimum speed of the generator below which the generator won't build up. Here you can make this is the maximum voltage the machine can build up. Let us say below NC you are rotating the machine. If you rotate below NC, how is the OCC? Below that. So where is point P now? Somewhere here in the residual voltage region. So finally we say at this speed, what is the maximum voltage the machine can build up? Means only residual voltage. That is itself is maximum, means no build up of voltage. So we are at this critical position, this particular thing. Now within 3 steps, simply you can calculate RC/NC of a given machine. First, plot OCC. Once this I have summarized. First, plot OCC. Second, plot RSH line. Third step is plot tangent to OCC. After these 3 steps, make a point R somewhere here, drop a perpendicular, it will cut original field resistance line at a point S. So RT in volts by OT in amperes is RC. RT represents OCC at N. Length of ST represents NC. Once see that curve. If you plot OCC at NC, this is OCC at NC. This one, this line. So simply you can calculate ST by RT into that speed. Always ST is less than RT, so NC you will get less than N. Only 3 steps. Plot OCC, plot field resistance line, plot tangent to OCC. Finished. Somewhere here, make a point R. Drop a perpendicular. It will make point R here. It will cut field resistance line at a point S. This is T. Sufficient. RT represents rated speed, given speed. ST represents ST always represents critical speed only. This length represents critical speed. Why? Because if you observe, the curve come down. Finally, if it drop down, automatically, no. That's why this is the critical. So automatically, ST represents critical speed. So RT by OT gives you, V by I gives you resistance, critical resistance, and from this ST by RT to that N, you will get NC. Here, one important point is, for a given machine, listen. For a given machine, let us take this machine. 1500 RPM is rated speed. It is given 1500 RPM is rated speed. And for this machine, in the manual, you are given like this. 900 RPM is the critical speed. So given like that. Which means you have to operate always this machine at 900 or above 900. Below 900 if you operate, you won't get any voltage. Only 6 to 8 volts, the residual voltage will be there normally. That is the meaning of that. Now, for this machine, you will be given critical resistance at a given speed. For this machine, you will be given critical resistance at a given speed. For example, if the machine is running at 900, it will excite. Above 900, it will excite. Below 900 it won't excite. Means there is only one value for critical speed for a given generator. Yes or no? There is only one value of critical speed for a given generator. It is 900, only that. If you operate the machine above 900, it will operate. Below 900, it won't excite. That is the meaning, only one value. Like that, you don't have one critical resistance value. Critical resistance depends on operating speed of the generator.
Why RST or collision?
Why?
RST or collision?
RST?
RST.
This one. If you don't like this point, make this point. Let me tell you, if you don't like this point, make this point. But all are same, you will get the same value. Because this is linear, this is linear.
So then how S is the critical?
How S is critical means, what is this line actually? What is this line? You have to tell me, what is that line? Now stand up. You have to tell me, what is that line? RSH line. If OCC come below RSH line, then no build up. So what is critical value? OCC and RSH are making a tangential point. That's critical value, right? As you said, this is RSH line, OCC critical value, tangent point. Similarly, when OCC come down, this OCC is making a tangent to original RSH line. So tangent means somewhere in this point, right? So what is S now? Sit down. If it's not get clear, you can meet me after the class. Right now. Critical speed for a given machine, is only one value. Critical speed for a given machine is only one value. But the critical resistance depends on operating speeds. Change the color of the pen. Continue. Critical resistance is directly proportional to. Critical resistance is directly proportional to operating speed of the generator. Directly proportional to operating speed of the generator. Listen carefully, here there's a logic very important. If a machine has 900 RPM critical speed, if a machine has 100 ohms shunt field resistance, if a machine has 100 ohms shunt field resistance value, let us say this is OCC at 1500. Listen, you want simply the critical resistance, not original field resistance, critical resistance of this machine. What you will do simply? Plot a tangent. You have to plot a tangent. And somewhere at this point you will mark a point R. You will drop it down. And this is R, this is T, this is RT by OT, you got the resistance value. Right? Now, you know, let us say this RT by OT, let us say this value is some 250 ohms. Let us say that, 250 ohms. Next. This machine, can it operate at 1200 RPM or not? can this machine be operated at 1200 RPM or not? Yes, because its critical speed is only 900. Above 900 you can operate at any speed. So let us say this machine is operated at 1200 RPM. Then if you plot OCC, how you will get? If you plot OCC, so this is OCC at 1200 RPM. Now, what is critical resistance? What is critical resistance when the machine is operating at 1200 RPM? What you will do? Will you say the same value? No way. What you will say? You have to draw again one tangent, and again you have to make a point and something like this, right? Let this machine operate at 1000 RPM. Let this machine operate at 1000 RPM. What is critical resistance? Is this value? No. What you will do? You will plot a tangent, you will make a point like this. Let this machine operate at 900 RPM. Let this machine operate at 900 RPM. What is the critical resistance? It is original shunt field winding resistance. Let us say this is 1000. This is 1000. Now you see this diagram. Plot OCC at 900 RPM. What is 900? Critical speed. Critical speed. Now you want what is the resistance, critical resistance of this machine. What you will do? You will plot a tangent. I am repeating here again. Let us make it. You are plotting OCC at 900 RPM. Let 900 RPM is nothing but NC. Then what you will do? I am asking you, what is the critical resistance of this machine when it is operating at 900 RPM? What you will do? You will plot a tangent and you will get a point. You will get a point. So you will make this value, you will make this value. What is the resistance you will get? Here you will get something, here you will get something. Finally you come here and what is the resistance? You carefully examine. It is nothing but shunt field resistance line only. Yes or no? So RC is nothing but RSH when the machine runs at critical speed. Critical speed. If you increase the speed of operation of the generator above critical speed, what is happening to RC value? Is it the same value or increasing? Increasing. If you see, the resistance value is increasing. If the machine is running at 1000, definitely it is more than that. If the machine is running at 1200, it is definitely more than that. So the critical resistance value is nothing but the shunt field resistance value when the machine is running at critical speed. From critical speed, as you operate above that, automatically critical resistance will increase. That is what you have written there. The critical resistance is directly proportional to the operating speed. Question number 10 from workbook. Once listen. Once listen. This is OCC at 1500 RPM. If you want critical resistance, you will plot a tangent to OCC. This is RC, you will say. Some point, let it be here. This is that value, this is this value, right? Now, machine is operating at 1200 RPM. RC value is something here. Let us say this is 200, this is 1. Let us say RC is 200. Now, OCC came down. (1200 RPM). If you want critical resistance, what you will do? What is the critical resistance of the machine when the machine is running at 1200 RPM? What you will do? Draw a tangent, right? So somewhere make a point. It is linearly varying. So let this point be this, right? Now, what is the critical resistance? What is the critical resistance? Is it above that or below that or same value? Definitely below it. If it is 200 by 1, it is likely to be 150 by 1. So what happened to critical resistance? Decreased. Next, you reduce the speed of the generator. Thousand. So what is the critical resistance? Again, you have to plot. You have to plot a tangent. Somewhere here to mean. So make it. So what happened to critical resistance? Decreased, right? So what is the conclusion now? Critical resistance of the machine depends on operating speed. NC is one value for a machine, 900 is one value. If you operate above 900, it will develop. But RC depends on different speeds above NC. What is the critical resistance of the machine when the machine is operating at NC? It is nothing but its original field resistance. When the machine is running at its critical speed, you cannot increase the resistance of the machine. Is the point clear? When the machine is running at critical speed, you cannot increase the field winding resistance. If you increase, it can't develop anything. What's the answer for question number 10? Simple. C. Proportional. It is C. (66) Self-excited DC shunt generator driven by its prime mover at rated speed fails to build up voltage across its terminals at no load. What reason can be assigned for this? The field circuit resistance is higher than the critical resistance. The initial shunt field MMF does not assist the residual magnetism. Between A and B, you have to pick one. Don't pick A if you are given B. There is a priority basis. First and foremost condition is residual flux. First preference should be given to residual flux. If it is not given, let us take, there is residual flux. So, once there is residual flux, it is not the end of the story. The residual flux, conductors will cut it, current comes into picture. The current first, when it enters into the field winding, it should not erase the residual flux. means the field and armature should be properly connected. Then only the loop, the build-up starts. After that, critical resistance, critical speed, everything. So first preference should be given to residual flux. Second preference, field and armature properly connected. The initial shunt field MMF does not assist residual magnetism. Why it is not assisting? Why it doesn't assist? When the field is not properly connected. Take a problem. In your notes, take a problem like this. Write down. Self-excited generator. Self-excited shunt generator. Self-excited shunt generator. Building up voltage normally. Building up voltage normally. If its field terminals are reversed, if its field terminals are reversed, option A, doesn't build up voltage, doesn't build up voltage. B, build up voltage normally, build up voltage normally. C, build up voltage in negative polarity, build up voltage in negative polarity. Now, let us consider the generator is building up voltage normally. Let this be terminal F, let this be terminal F. This is A, initial condition. Normally the build-up is taking place. Means the current which is flowing from A to F, F to FF is assisting, is adding the residual flux and the build-up is taking place. No problem. Now what is given in the problem? Field winding is reversed. Means this is reversed means previously current is flowing from F to FF. Now the field winding is reversed. It is FF and this is F. Now again, if it reversed, what happens? The current flowing into the field winding is flowing from FF to F in the reverse manner. What happens? If you want to make the flux to negative, for example, first one polarity, opposite polarity. So, while doing so, it will make the flux become zero. At one instant, at a particular instant, it will erase the residual flux also. Once the flux becomes zero in the machine, at that instant, you just think there is no stator. If there is no flux, what is the meaning of that? At that instant, no flux means no poles, no stator, only rotor, rotating. What is the EMF induced there? Zero. Not even 6, not even 8. It is simply zero. Another question. So doesn't build up voltage. Or in the options, if you are given 0, pick 0 voltage. Next question. If the direction of rotation is reversed, if the direction of rotation is reversed, what's the answer? let us say, for one direction of rotation, build-up of voltage is taking place. If you are given in a question, direction of rotation is reversed, what happens? Let us think in the first condition, the field is connected like this. One direction of rotation. The polarity of induced EMF depends on the direction of rotation. So, let us say, for this direction of rotation, the current is coming out and it is flowing like this. Current is coming out, it is flowing like this, so assisting, no problem. Now, if you reverse the direction of rotation, what happens? Previously you have done clockwise, the current is coming like this. Now, if you reverse the direction of rotation, the polarity of the induced voltage is reversed or not? Definitely reversed. So if the polarity is reversed, automatically is the current coming like this or it will go like this? Definitely it will not come like this. Previously this is plus, this is minus. Now this is plus, this is minus. So the current flows like this. So what happens now? It will neutralize the residual flux, no build up. The polarity of induced EMF depends on direction of rotation. Now, next question. Both field winding as well as direction of rotation reversed. Right? Both field winding as well as direction of rotation reversed. What is phi? What is n? Phi is flux, n is speed. One type of rotation if you take plus, for the other rotation you take minus. Flux for one polarity if you take, for one FF if you take plus, if you reverse the field bending you should take minus. Previously either one is reversed, so there is a problem with the self-excited generator. But here what is happening means, now once listen here, the field winding is not reversed here, direction of rotation is reversed. That's why when the current flows like this, the residual flux has been erased away. Now imagine direction of rotation as well as field winding also reversed. Means F come here, FF went there. So like in the previous case, current is flowing from F to FF. Here also current is flowing from F to FF. Will the residual flux be assisted or not? Yes. There is no neutralization of residual flux in this case. So no problem with the build-up of voltage. But what is happened here? Flux is reversed automatically. Speed is reversed. So minus, minus. What is the voltage? Say positive. Build-up voltage normally. Question number 2, workbook. Listen, in this question, it is given the field circuit switch open, closed. When it is open, voltage across the armature is 8 volts. That is what given. Open in all the three cases when the field is not connected. Forget about the field winding. It is not connected to any supply. It is not connected to this. Just the armature is rotating at rated RPM. So there is 8 volts means there is some residual flux in the poles, due to which you have 8 volts. If you observe, in all the three cases, open 8 volts means what is there in the machine? Residual flux. Residual flux is producing 8 volts and it has been completely erased away, so the voltage became 0. Why this voltage became 0? What could be the reason? Only one reason, that is 3 only. Only one reason, that is 3 only for this. No other reason. Yes or no? Next. You are clearly given the minimum value 8 is here. When the field circuit switch is open, you got minimum value, that is 8, that is residual voltage. You know, if the resistance of the field winding is greater than the critical resistance, what will be the voltage across the machine? It's a residual voltage, a minimum value. So, if open 8, close is also 8, what will be the result? Same values. What it is representing you? It is representing again 1. It is representing the same thing, 1. So if 1 and A and C are matched automatically, we should be matched. If you observe, in the second, it is given critical load resistance. Load resistance is some above or below some critical values. We don't know what is 12, what is 10, 10.5, 15, 20. There is no theory to explain. There is a theory to explain minimum voltage, maximum voltage. Between that, there may be some reason which makes the voltage to some 12 volts. For example, let us say load has some value. Due to that load critical value, as it is decreased, the resistance, what happens? The current will be flowing into that and into the field winding. Due to which the flux and all those things will be varied, and automatically you are getting some voltage above minimum value. So automatically it is for 2 only. The context of the question is, how the question is framed means, you have to pick 1 and 3, automatically second one will be matched. Keep the heading. Voltage build up in series generator. Answer is A. Voltage build up in a series generator. What is the first and foremost condition for a self-excited generator to build up voltage? In any machine, residual flux. That's the replacement of a big generator across the field winding. So, residual flux necessary, first and foremost condition. Now, listen. Let us consider in a series generator, to the pole, you did field flashing, therefore some residual flux is there. Now you start rotating the machine. When you start rotating the armature conductor will cut that flux, and what is produced? EMF is produced. How much? Let it be 6 to 8 volts. EMF will produce. Now, will there be any current flow in the machine? Is there any current flow in the machine? No, because this is a series machine which is open, no load. So, even though there is 6 to 8 volts, the circuit is not closed, so no current will flow, and it will remain like that only. If you don't load, if the load is not connected across the terminals, the machine won't build up any voltage. The best condition for a shunt generator to build up voltage is it should be on no load, and that's the worst condition for a series generator. Yes or no? Because if the machine is on no load, across the terminals if there is no load, no current will flow into that. So series generator should be started. If you want the voltage build up, then you have to connect some load across it. Loading means what? Loading, you are loading across those two terminals means you are reducing the resistance across those two terminals. Yes or no? You are just reducing the resistance across those two terminals means you are increasing the current actually. You are making the current to increase in that particular path. So let us consider the series generator has connected some load. Loading means automatically load the current is flowing in the machine. So let us consider with some load you are starting the machine as the machine is loaded. When the machine is loaded, automatically what flows in the load? Load current IL. So from where this current is coming from? It is coming into the field winding from the armature. So IA, ISC, all are same. So when you connect the load is demanding current from the armature. It is drawing current from the armature. The current will flow from the field winding, and automatically as the current increases, flux will increase and automatically voltage will increases. Is the point clear? So now you can't say IF is on the base, it is IA. So when there is no current, for example, what will be the voltage? 6 to 8 volts. So slowly as IA develops, automatically what happens? The voltage will rise and it becomes saturated. As you keep on loading the machine up to a load value, up to a field current value, only the flux will increase. But after that the flux becomes constant, and same thing you will observe here. But from no load to full load condition, what is the voltage across the generator? Is it constant or varying? From no load to rated load. No load to rated load. Let it somewhere here, rated load. In this region, what is the voltage across the series generator? Is it constant or varying? It is varying. It is a variable voltage generator. It has rising characteristics. This is not suitable for normal power supplies. You require a constant voltage across any load, across a fan, across a bulb or any load, you require a constant voltage. If the voltage is varying, automatically the bulb fluctuates, the fan speed will fluctuate. Like that, you require a constant voltage across any load. But what is happening to the series generator voltage, terminal voltage? It is rising in nature. It's a variable voltage. That's why it is not at all useful for normal power supplies. It has a specific applications. Later we'll discuss the characteristics. But here, write down some points. The necessary conditions are similar. The necessary conditions are similar. Number one, residual flux. Residual flux. Number two, some load should be connected across terminals. Some load should be connected across terminals. Number three, field armature properly connected. Field armature properly connected. The total resistance of the circuit. The total resistance of the circuit should be less than critical resistance. Right, like this. RA plus RSE plus RL should be less than. You can't divide now. Listen, previously in a shunt generator, the initial current is flowing into which winding? Shunt field winding. So you are limiting that. The shunt field winding, when the initial current flows, the field winding should not be more than this value. If the current, if the resistance of the field winding is more than that value, the current can't enter and it won't build up voltage. The field winding resistance is playing a vital role here. In this particular machine, when it starts build up, when you connect some load, the initial current is flowing through which resistance? It is not one resistance here. The current is flowing through RA, the current is flowing through series field winding, the current is flowing through load resistance. You can't break it now. You can't say simply the resistance of the series field winding should be less than. No. The current, the initial current is flowing through all the loop. So all the resistance of this loop should be less than critical resistance. For example, if you want to calculate critical resistance of this generator, how do you calculate? You have to plot OCC. You cannot plot OCC for a series generator simply. If you want to plot OCC, then again you have to separately excite it. Field winding should be separated. You have to apply voltages and you have to connect a voltmeter. You have to calculate. So like that, if you do, if you have a OCC, again what you will do, you will plot a tangent. So then what you will do, you will make a point, you will make a line like this. So RT by OT, same process, same process. Then what you will say, this is the critical resistance of the series generator. And while representing the total resistance of the machine and the circuit should be less than critical resistance, because the initial current is flowing through the entire circuit. Next. The speed of the generator. The speed of the generator should be more than critical speed. Speed of the generator should be more than critical speed. So the difference between shunt and series is, shunt generator best condition should be on no load. Series generator best condition should be with some load. Here comes the turns concept. You have written for series generator, you require thick conductor with less number of turns. Why you are making large number of turns in a shunt generator? What is the reason? The initial current flowing is very small value. So to get good amount of initial MMF, to assess residual flux and to develop the loop, cumulative loop for successful build-up, you are intentionally making large number of turns. That's the concept. Here, the initial current is due to load. The initial current is due to load. Yes or no? In series machine, the initial current is coming because you are loading the machine. Yes or no? It is not simply coming like this. Some voltage is developed in the armature, that voltage is producing. It is not that. You are making some load, so you are reducing the resistance of the path. What is the resistance here? Very huge, a small current. You are reducing the resistance of the path and the initial current is very high. Very high in the sense, compared to this, the current is in this is good value. So when the current is, initial current value is very good, no need of large number of turns. And as you start loading the machine, automatically the current value will increase. If you observe in the shunt field winding, the current value is maximum 1 ampere, not more than that. But what is the range of the field current in the series machine? It is nothing but load current only. If load is 10 amperes, 10 amperes flow in the field winding. If load is 30 amperes, 30 amperes will flow in the field winding. Here, if the load is 30 amperes, what is the current flowing in the field winding? Only 1 ampere. Is the point clear? That's why in a series machine you require less number of turns with thick conductor. Here you require large number of turns with thin conductor. Keep reading. Compound generator. Subheading compound generator. A compound generator on no load, right now. A compound generator on no load is equivalent to shunt generator. Therefore, voltage build-up. Process is identical. Voltage build-up process is identical to shunt generators only. Identical to shunt generators only. So all the conditions are same, everything is same. Because you know on no load, shunt generator and the compound generator are same. Series flux is negligible on no load. Series flux comes into picture with the load only. On no load, the current flowing through the armature and the series field winding is very small. So there is phi SH, there is phi SE. So on no load, the current flowing through the armature is very small. So what is series flux value? Very less, and this is negligible. So now what is the machine? There is nothing but shunt machine. Everything is same. The next topic is very important: armature reaction. Now, listen, if you take a separately excited DC generator, the current flowing in the armature and the current flowing in the load is same. In a separately excited DC generator, IA is equal to IL. Yes or no? In a shunt generator, IA is equal to IL plus ISH. In a series generator, IA is equal to IL. In a compound generator, IA is equal to IL plus ISH. These are all the generators, DC generators. Separately, shunt, series, compound. Next. What is ISH value? It is V by RSH. This value is low and constant, nearly constant, compared to IL. Yes or no? Compared with IL means if a machine of rating 20 amperes or 30 amperes or 50 amperes, as the load increases or load decreases, ISH remains same as 1 ampere only. So IA is 50, let us say 50 is equal to IL 49 plus 1. So IA 50 is equal to 49 plus 1. Finally, what I want to convey is ISH is low value compared to IL. So, can you neglect for analysis? Finally, the load current is nothing but armature current, right? when you load the machine, it may be a generator or a motor, the load current is nothing but armature current. Whenever you say armature current, it is due to load. Whenever you connect some load, that load is current is flowing from the armature. Both of them. Now, what is armature reaction means? Until now we have been discussing regarding the machine on no load. When a machine is on no load, there is main flux in the machine, which is working flux. We have written the purpose of the pole is to provide working flux. There is working flux in the machine, and as there is no load, there is no armature current. As there is no load, there is no armature current. If you think there is armature current, small value, negligible value. So, in the machine, there is stator, there is rotor, there is air gap of 1 mm. In this air gap of 1 mm, the main flux, working flux is uniformly distributed throughout the peripheral of the armature. If there is no load, there is no problem in the machine. Problem comes with the load, with the current. Once the machine is loaded, the armature conductors carry load current proportional to load current. So, as the load is increasing, the current flowing in the armature conductors also increasing. In the armature, what are there? Turns are there. Armature is made up of winding turns. Those are conductors basically made into turns. So when current flows in the turns, what is produced? MMF. When MMF is there, immediately it will produce its flux. So where is this flux now? This flux is also on the armature. Where are conductors? Conductors are on the armature. So on the armature conductors, what will be there? Flux. If there is a magnet, on the magnet what is the flux? If there are conductors carrying current, according to oil stud, when a current carrying conductor is there, around that what is the flux? So there is main flux in the air gap. When the machine is loaded, there is armature flux in the air gap. Why armature flux is coming into picture? When load current flows through the armature having turns, armature current into armature turns is armature MMF that give rise to armature flux, which is in the same air gap. Now, in this 1 mm air gap, there is main flux, there is armature flux. They will interact, they will react each other, and that reaction is armature reaction. Right. When the machine is on no load, armature current is negligible. Armature current is negligible. There will be only main flux. There will be only main flux distributed uniformly throughout the armature. In the air gap. When the machine is loaded, load current flows through armature conductors. Load current flows through armature conductors. And it turns, produces armature MMF, and armature flux, which is also distributed throughout the peripheral, which is also distributed throughout the peripheral of the armature. In bracket, in the air gap, in the same air gap. Change the color of the pen right now. The effect of armature flux on main field flux distribution in the air gap is called as armature reaction. It has two effects in the machine. Cross magnetization, demagnetization. Listen, as the name implies, cross magnetization, the meaning is distortion of flux. Cross magnetization means distortion of flux. Write on that. Cross magnetization, distortion of main flux. Cross magnetization means distortion of main flux, which affects commutation process. By shifting MNA. Which affects commutation process by shifting MNA. Magnetic neutral axis, MNA. Demagnetization is reduction in flux. Demagnetization is reduction in flux, which reduce induced EMF or terminal voltage. Induced EMF or terminal voltage. Now, in order to understand these two concepts, how they are exactly happening in the machine, let us consider three simple diagrams. In the first diagram, we consider only main flux. In the second diagram, we consider only armature flux. In the third diagram, that's a live condition, we will consider both fluxes, what are happening in the machine.
Leakage. Slipping. There are some. क्या कर रहा था? वही देख रहा था। मैं भी 4:30 में सोया मैं भी 4:30
Listen, there are two axes. One is G and A, and the other one is M and A. G and A means geometrical neutral axis. Means you can take like axis of symmetry, center of the machine. Is the point clear? Geometric neutral axis means it is the axis of symmetry or center of the machine. Similarly, there is M and A. If the flux lines are moving like this, where is M and A? Across points 1 and 5, if you draw a line, that is M and A. We discussed already. So, G and A, M and A coincide each other if there is only main flux in the machine. Can we say that? In this particular figure diagram, I am showing only main flux flowing from north to south, always like that. If there is only main flux, means the machine is on no load. Assume like that. Machine is on no load. If there is only main flux, M and A, G and A coincides with each other as the M and A is at 90 degrees to the flux lines. So M and A is always making 90 degrees with the flux lines. Next. You know that the brushes are always placed on M and A. Actually, they are on the commutator outside. Now, in the second diagram, there is main flux already. I will maintain one standard for entire DC machines. I have taken North Pole, South Pole generator rotated clockwise. According to Fleming's right hand rule, if you stretch your three fingers like this, right hand rule is to apply to a generator. If you stretch your three fingers like this, then clockwise notation. The conductors, when they are under the influence of North Pole, what is the notation in them? Cross. Now, the same conductors, when they come under the influence of South Pole, they will have now we want the armature flux, how it is. If the current is going away from you, and not all these conductors going away from you, so if you hold like this, how are the rest of the fingers telling you? This is the current direction, the fingers are telling you which direction? Clockwise or anti-clockwise? Clockwise, right? Actually, the flux lines are concentric circuits. Like this. So we are interested inside what is happening, right? This particular part. So now we will give a direction. Similarly, when it comes to the conductors lying under the South Pole, what is the direction of rotation of flux? Anti-clockwise. It's coming outside. So thumb indicates the current. So now it is anti-clockwise. Again. On the armature, observe how is the flux on the armature. It is moving exactly downwards. Armature flux. Now, the armature flux will interact, will take an action on the main flux coming out of the poles. That is what is called as armature reaction. So now, in the third diagram, we will consider the main flux as well as armature flux. For your understanding, we consider them differently. In the first figure, you consider only main flux. In the second figure, you consider only armature flux. You won't get only armature flux without main flux. When main flux cuts the conductors, voltage is induced. You are loading it, current flows. So, to understand how exactly is the armature flux, you can just separately. But practically, what will be there in the machine? There is main flux, there is armature flux simultaneously in the air gap. Now, this is the main flux flowing from north to south. In the third diagram, we represent both fluxes. Next, listen. Listen.
बोलिए सर बोलिए बोलिए फंसा तो फंसा
Now, depending on the direction of rotation, you are going to define the pole tip. Means from this point to this point of a south pole is called as leading pole tip. The first pole tip, in the direction of rotation, first which it meet. For example, it is the direction of rotation. South pole is here. The first pole tip in the direction of rotation when it meets is known as leading. The next pole tip is trailing. Similarly, this pole tip is leading. And the next pole tip is known as trailing. The defined or the naming depends on direction of rotation of the machine. Since it is rotating clockwise, you have named leading, trailing for the south pole, leading, trailing for this north pole. If the machine rotates anti-clockwise, what will be the naming of the pole tip? If the machine rotates anti-clockwise, this becomes leading, this becomes trailing. So I'm fixing a standard. I'll follow the same thing throughout the entire machines. So first diagram and this diagram are same. Observe. Now, why you have defined like this means there's a reason for that. If you observe, the armature flux and the main flux under the trailing pole tips region, the flux density is increasing. There is a magnetization taking place under the trailing pole tips of the generator. Observe the diagram. Why you have named like that means there is a reason for that. You observe under one pole half, particularly trailing pole tip. This trailing pole tip, that trailing pole tip. Under those two trailing pole tips, if you observe, the armature flux and the main flux are in the same direction. Yes or no? Yes or no? Once recollect cumulative compound generator. How is phi SH, how is phi SE in a cumulative compound? Once recollect cumulative compound generator. How is phi SH, how is phi SE? Same direction. So what is the net flux in the machine? Phi SH plus phi SE. Similarly, when armature flux and the main flux are in the same direction in this particular region, then what's the net flux? Both are adding each other. Both are adding each other means what happens to the net flux in the machine? Increasing. Similarly, under this trailing pole tip of the south pole, both are in the same direction. So what happens to the net flux? Increasing. So under the trailing pole tip, the net flux is increasing. Magnetization is taking place. Now, see what is happening under the leading pole tips of the generator. If you see under the leading pole tips, the main flux and the armature flux are quite opposing in nature. Once like differential compound generator, phi SH is in this manner, phi SE is in this manner. What is the net flux in the machine? Phi SH minus phi SE. Similar to that. When main flux comes like this, when armature flux comes like this, what happens here? Demagnetization. When main flux comes here, armature flux comes here, demagnetization. So, under the trailing pole tips of the generator, there is magnetization. Under the leading pole tips of the generator, there is demagnetization taking place. Now comes the question. For example, let us consider under the trailing pole tips, the flux density has been increased to some extent. Under the leading pole tip, the flux density will be decreased to the same extent. Yes or no? In this region, if you say flux density increased, in this region decrease, if the increase is equal to decrease, what is demagnetization? There is no demagnetization. Is the point clear or not? If the increase under the trailing pole tips of the flux is equal to decrease under the leading pole tip, then what is the net demagnetization, total demagnetization? Zero. Yes or no? For example, it's like this. If I have 100 rupees in this pocket, if I have 100 rupees in the pant pocket, if we remove 100 rupees from here and we keep it here, what's the total money with me? Same 200, right? There is no loss in the money, right? Same thing is happening here also. Under a pole, some flux is demagnetized here, the same amount is magnetized on the top. So what is demagnetization? There is no demagnetization, right? Similarly, here there is some demagnetization and there is some magnetization here. So what is the total demagnetization? But the flux is cross-magnetized. The flux is cross-magnetized. You can't have the same flux like this now. This is the flux in the machine when there is no armature flux. But when the armature flux comes into picture, this flux won't come like this, but it will get distorted, it will get disturbed, it will get cross-magnetized. Why cross-magnetized means, if you observe here, there is a demagnetization in this region, as well as there is demagnetization in this region. So, the net flux won't flow like this and like this, but there is magnetization in this region. The lost flux here came here, the lost flux here again came here. So here the net flux density has been increased in this trailing pole tip. What will be the flux path now? Is it the same path like that? Just imagine, will the flux flows like this only? There is opposition here, there is opposition here. So what will be the flux path in the machine now with the presence of armature flux? It will cross-magnetize like this. If you are asked, what is demagnetization in this particular case? We can expect demagnetization only due to saturation of the pole. Only due to saturation of the pole there will be a slight demagnetization, only that. For example, if the amount of increase is equal to amount of decrease, what is the net demagnetization? 0. If the amount of decrease is more than amount of increase, will there be demagnetization or not?
Yes.
Definitely it will be, right? Means increase in the flux is only 0.9 Webers, decrease in the flux is 1 Weber. Is the point clear? Decrease in the flux is 1 Weber. If increase in the flux is also 1 Weber, there is no demagnetization, just cross magnetized, only that. Only that. Previously, 2 Webers flux is flowing uniformly distributed. Now, 2 Webers flux is flowing like this. 2 Webers flux flowing in this manner. 2 Webers flux flowing in this manner. Is there demagnetization? No. No reduction in flux. Magnitude is same. But what happened to the axis? Shifted, disturbed, distorted. But let us say decrease in the flux is 1 Weber, increase in the flux is only 0.9 Webers, let us say. Then is there any demagnetization?
Yes.
So only 1.9 Webers is flowing like this, right? So there is a demagnetization. Why is this demagnetization coming into picture? Means saturation. You know, when the poles get saturated, once they are under saturation condition, to get an increase, they are reluctant to increase, but decrease has no problem. For example, when you are saturated, if I want to continue the class, definitely you will be reluctant. If I leave the class, no problem. Same manner, when the pole is saturated, if you want to increase the flux in one pole half, they are reluctant to the increase, but when the pole is under saturation conditions, there is no problem with the decrease. Is the point clear? For decrease in flux, there is no problem with saturation. So decrease will be there, but the same amount increase will not be there. So due to saturation of the trailing pole tips in a generator, due to saturation of one of the pole half in a generator, there will be a slight demagnetization. Right now. Listen, mathematically, phi A, phi F are like this. What is the net flux? Net flux? Can you say this, net flux? This is net flux when there is no armature flux. When there is armature flux, this flux is becoming like this. Can we say that? These two are mingling each other in a machine, reacting each other, and due to armature reaction, the net flux, the main flux became like this. Yes or no? See this axis. See here, that one. The flux is like this is phi F. Listen, if the flux is like this on the armature, this is phi net. What happened to the flux in the machine? Is it distorted or not? Is it distorted or not? It is not in the same horizontal line like this, it is distorted. Now, where is MNA? You know, this is MNA here, no doubt. But is the MNA same in this particular case? No. Where is MNA? Definitely shifted to some angle theta, no doubt in that. Means, in this particular portion, there is no zero now. The flux lines are moving parallel somewhere in this point, somewhere in this point, right? So, this is means MNA is always making 90 degrees with flux.
सामने तो लगता है बलात्कारी हो गया ये क्या था?
Right on.
एक मिनट सर एक मिनट वो कहते हैं वाइट ना
Depending on the direction of rotation. Depending on the direction of rotation. The pole tips are defined. The pole tips are defined as leading and trailing pole tips. Leading and trailing pole tips. The armature flux under the trailing pole tips. The armature flux under the trailing pole tips is magnetizing in nature. Is magnetizing in nature. And under the leading pole tips, it is demagnetizing. Under the leading pole tips, it is demagnetizing the main flux. Consequently, the main flux gets distorted. The main flux gets distorted, which shifts MNA, in the direction of rotation of generator. Underline. In the direction of rotation of generator to some angle theta. To some angle theta. If the magnetization and demagnetization, if the magnetization and demagnetization under a pole is equal, under a pole is equal, there is no net demagnetization, there is no net reduction, there is no net reduction in flux. Only distortion. Only distortion. Change the color of the pen. Due to magnetic saturation, due to magnetic saturation of the trailing pole tips the demagnetization under leading pole tips is slightly more than magnetization under trailing pole tips. Therefore, there is slight demagnetization. Now listen, one important point here is you have two types of demagnetizations. One demagnetization you have written here, that is due to the magnetic saturation of the pole half. This is one form of demagnetization, which is a small value. It may have a value but general negligible. But you have one more demagnetization which comes from the brush shift. Right on. The brushes are always placed on MNA. For successful commutation. In order to improve commutation, the brushes need to be shifted. Onto new MNA. In the direction of rotation of generator. Underline. This leads to additional demagnetization. Keep the subheading, effect of brush shift. Until now, we have been discussing regarding the armature reaction effect. You know, armature reaction is the effect of armature flux on main flux. So, if there is main flux, no problem. But due to armature flux, the main flux is distorted. So, as there is distortion, automatically MNA is also distorted. So, now this is MNA. This is MNA means the pressure should be shifted on to this particular point. So, in order to improve commutation, so when you place the brushes here, then automatically this is the neutral zone. All these conductors are under influence of one pole, these conductors are under influence of the other pole. Now the concept is, with the brush shift, there is additional demagnetization that you have to understand. Demagnetization means one is due to the magnetic saturation and the other one is due to brush shift. Brush shifting concept is not there now. It has been totally eliminated once the interpoles were invented. Brush shifting is not done in DC machines now. Already the interpoles were invented, and the interpoles are improving commutation far better than a brush shift, because with the brush shift there are many problems. So we will be discussing that in the commutation topic. What are the methods to improve commutation? Brush shifting is the first form or the first method to reduce armature reaction effect or to improve commutation. That's the way it is. This is a topic important for only competitive exams, but generally this is not done in any DC machines. Now we are not shifting the brushes. But what is happening here means, let us consider you understand this diagram? The brushes are shifted onto MNA to some angle theta to improve the commutation. Previously this is GNA MNA. Now MNA has been shifted to some angle theta. So brushes are shifted in the direction of rotation of the generator to just improve the commutation. Then this is the neutral point, this is the neutral zone. So what we consider, all these conductors are behaving as now listen. In this theta region, if this is theta, this is also theta, right? This theta region on the machine, you see the entire machine, don't see only this part. In this entire machine, this theta region and the same region here. If you plot an axis, this point where the brushes are located, similarly this point. Listen, the problem of the brush shift comes with theta. The problem of brush shift comes with theta. If theta is 0, there is no problem at all. Remember this. If theta is 0, means what is the meaning of that? Theta is 0 means the brushes are not shifted. Brushes are on GNA here only. With theta, everything is coming into picture. Remember that. So we are concentrating on theta now. So this theta region in the entire machine, don't see only on the top. This entire machine in the armature, if you say this is theta region and the entire theta region here, and in this theta region, the entire theta region here, what is happening means the conductors lying in this region, the conductors lying in this region, how much this is? 2 theta. This is how much? 2 theta. If you say this is theta, if you plot an axis like this, what is this angle? Theta. What is this angle again? It is also theta, right? Now, why you made this line means to represent problem is coming with theta. So, what is happening in this region conductors, in this region conductors, in these conductors and in these conductors means, if you see, if you put a thumb rule, the conductors are going into, right? Into means, how is the flux, clockwise or anti-clockwise? Clockwise flux. So, some clockwise flux. And this, the conductor is coming out, so who is the flux? Anti-clockwise. So, in this region, the theta is offering demagnetization. You understand more clearly in the diagram, the vector diagram. The problem comes with theta. So investigating theta on the entire armature at the top and the bottom, as well as if it is theta, this is also theta. In these conductors, in this particular axis, the entire theta region, in total 2 theta and 2 theta region conductors, these are offering demagnetization. Actually, when you say these are all the conductors on the influence of North Pole, how is the armature flux? Like this. Here armature flux is like this. So, when the brushes are not shifted, brushes are on MNA, how is armature flux? See the second diagram of your notes of armature reaction. Brushes are not shifted. How is the armature flux? It is just downwards along MNA, right? So what is armature flux doing then? Only cross magnetization. Slight demagnetization, that is separate effect, that is due to saturation. There is no brush shift. Now, what happened? This is MNA, new MNA. So brushes are also shifted onto new MNA. So how is the armature flux now? Is this armature flux or not? This is the armature flux. Is this armature flux what it will do to main flux? This armature flux, what it will do to main flux? It will have two effects now. Previously, when the armature flux is just downwards, it is only doing cross magnetization. It is only shifting the phi F to down. But now this phi A will do two things: cross magnetization as well as demagnetization. How? You will understand clearly. In this phi A, you can resolve into two components. One component is this one. If this is theta, this is phi A cos theta. Yes or no? Similarly, this is phi A sin theta. What is this means? Phi D. What is this means? Phi C. Now the armature flux can be resolved into two components. One component is opposite to phi F, known as demagnetizing component of armature flux. Another component is perpendicular to main flux, known as cross magnetizing component of armature flux. If theta is 0, what is demagnetizing component? 0. So the problem starts with theta. Is the point clear or not? So that's the reason why brush shifting is not done now, but that's the oldest method to improve the commutation. Better. Due to the brush shift, due to the brush shift,
Due to the brush shift, आगे सर
due to the brush shift, the armature flux has two components. The armature flux has two components. Number one, phi D, demagnetizing component of armature flux. Phi D, demagnetizing component of armature flux, proportional to sin theta. Which reduces main flux. Depending on brush shift angle theta. Depending on brush shift angle theta. Make a note. If there is no brush shift, if there is no brush shift, theta is equal to 0, sin 0, 0, phi d 0. What's the meaning of that? No demagnetization. No demagnetization. Listen now, once listen. No demagnetization means all the armature flux is cross-magnetizing in nature. Is the point clear? There is armature flux in the machine. In this armature flux, some part is doing demagnetization, some part is doing cross-magnetization. If there is no brush shift, then all the armature flux is doing cross-magnetization only. And continue that. Which means all the armature fluxes, which means all the armature flux is cross magnetizing in nature. All the armature flux is cross magnetizing in nature. Now keep number 2, phi c. Cross magnetizing component of armature flux. Cross magnetizing component of armature flux proportional to cos theta. Now, in the previous case, you substituted theta is equal to 0. When theta is 0, you said phi d is 0, but phi c is phi a. Phi c is phi a. What is the meaning of that? All the armature flux is cross magnetizing in nature. Let us take one more case. Brushes are shifted 90 degrees electrical. Brushes are shifted 90 degrees electrical. Remember, in electrical machines we are concerned about electrical degrees only. Let us take like this. Brushes are shifted 90 degrees electrical. Then what's the meaning of that? All the armature flux is entirely demagnetizing in nature and there is no cross magnetizing. Can we say that? It means, just imagine brushes are shifted here. So how is the armature flux now? If the brushes are here, this is the armature flux. If the brushes are here, how is the armature flux? Like this. So if this is the armature flux and this is the main flux, both are directly opposing, demagnetizing. See, if phi a is like this, it will only cross magnetize the main flux. Okay? If phi a is like this, it will only demagnetize the main flux. If phi a is like this, it will do both. Is the point clear? It will do both. The two things depends on the theta. Two things depends on theta. As theta increase, automatically demagnetizing will increase. Sin theta, theta proportional. So as theta decreases, demagnetization decreases. Make a note here again. If brushes are shifted to 90 degrees electrical, then if you substitute, you will get phi d is equal to phi a and you are getting phi c is equal to 0. What is the meaning of that? If you substitute in phi a sin theta, you will get phi d is equal to phi a. In phi a cos theta, you will get phi c is equal to 0. That means all the armature flux is demagnetizing. Said demagnetizing ampere turns. Demagnetizing ampere turns per pole. Observe that with theta there is demagnetization. Finally, the conclusion is the demagnetization is coming with theta. Therefore, the theta region on this top of the armature and in the bottom of the armature, as well as the theta region on the top and the bottom. The entire region, this region is taken into account for the demagnetization. When the brushes are shifted in this manner, this theta, as well as on the down also same theta. Similarly, axis shifted here, this theta as well as on the top theta. So this 2 theta as well as 2 theta region total. This 4 theta region is offering demagnetization. Demagnetization comes with the theta. So theta is the problematic area. So on the top and on the bottom total you will have 4 theta. So this 4 theta region out of total how many degrees? 360. If you observe, demagnetizing ampere turns per pole. Let's be very clear. We will say everything in electrical degrees. No concept of any mechanical degrees here. If you refer one book, it will be mechanical. If you refer one book, it will be in electrical degrees. You just standardize everything into electrical degrees only, because the basic heading is per pole. This topic, the heading is per pole. Under a pole, how many electrical degrees? 180. Always 180. Let there be 2 poles. Let there may be 1000 poles. Always. So no confusion now. So you just fix it as electrical degrees, everything, no problem. Is the point clear? Let us consider under a pole there are 180 electrical degrees. Let there be any number of poles in the machine. And if you split this armature for 2 poles, don't consider there are 2 poles, there is one GNA or MNA, here you are giving the brushes. This is true for any number of poles. If there are 4 poles, how many brushes? 4 brushes. If there are 4 poles, you will get 4 means this is, for example, this is 1 pole, if this is 1 pole, between this pole and this pole there is 1 MNA. Between this pole and this pole there is 1 MNA. How many points you got again? 4 points. You can place plus minus brushes. So if you shift one, all will be shifted. So we will be discussing armature reaction causes for 2 poles for understanding, and it is true for any number of poles. Same thing happens. Now the concept is under a pole always 180 electrical degrees. In this 180 electrical degrees, how much theta is doing demagnetization? So theta is also in electrical degrees only. Everything is in electrical degrees. Let it be. Out of 180 electrical degrees, out of 180 electrical degrees under a pole, 2 theta region is offering demagnetization. Yes or no? Under this pole of 180 electrical degrees, again 2 theta region is offering demagnetization. Can we say that? If there are 4 poles, if there are 4 MNA like that, 4 poles, in 4 regions also you are shifting the brushes. Under a pole, again how many electrical degrees? 180. So how much theta you will consider there? 2 theta, 2 theta. It is true for any number of poles. Now the concept is, let us consider, we will split this. This simply, you can split this in order to write the expression, demagnetizing ampere turns per pole, individually write. What is demagnetizing area in the entire armature? Since you are making per pole basis, let it be 180 degrees. Because you are telling per pole, let it be per pole, how many electrical degrees? 180. Next. In this total 180 degrees electrical, how many electrical degrees is the brush shift? Problematic area, how much? 2 theta. This is demagnetizing region. Next, ampere. Let us say IA is the armature current. IA is the armature current. Then, what is the current flowing in the armature conductors means? It should be IA by A. If you say this is the armature and If you say this is IA, generally what we say, the current out of the armature is IA. This is IA. So in the armature there is winding. In the winding there are parallel paths, at least 2 or 4 or 6 parallel paths. So when you have 2 parallel paths, I am representing like this. The winding you can take like this. The winding is in 2 parallel paths. Then you place 2 brushes. So if there is IA here, what is the current in this? IA by 2, IA by 2. 2 parallel paths, IA by 2, IA by 2. If there are 4 parallel paths, IA by 4, IA by 4. Let us make it generally, let there be a number of parallel paths. So what is the current flowing in the turns?
IA by A.
Why you have to write means, here there is a turn known as ampere turn. Ampere turn means if you write turns here, if you write there are Z by 2 number of turns in the armature, you have to write what is the current flowing in these turns only, not somewhere outside. Am I clear? Where is this Z or Z by 2? Inside. These are Z or Z by 2 conductors inside. So if you write turns, ampere turns, that product should be belonging to inside armature, not outside current into inside turns. So what is the current flowing in Z by 2 turns? It is IA by A. Demagnetizing ampere turns per. Simple. Why you are calculating this, you will understand later. Right on. The demagnetization due to press shift comes with theta. You mark like this. Let this be point O. Let this be point A. This point B. 2 points. The conductors lying in the region. OAP and OCD. The conductors lying in the region OAP and OCD offer demagnetization. The rest of the conductors means which region? OAD and OBC. What are they doing? Cross magnetization. The rest of the conductors are offering cross magnetization. In order to compensate this additional demagnetization, This additional demagnetization additional field ampere turns need to be provided on each pole, therefore demagnetizing ampere turns per pole are calculated. Therefore, demagnetizing ampere turns per pole are calculated. Listen. I'll give you, let me complete this. I can't stop this in between. Let us consider there is 5 Weber's amount of flux coming out of the North Pole. Out of a North Pole, already there are, let us say, some shunt field turns. Let us say 5 turns are there. These 5 turns are producing 5 Webers of flux, let it be, which gives you 220 volts in the armature. Is it clear? That's the condition of the machine. On no load, there is 5 Webers amount of flux, therefore 220 volts is producing, perfect the machine is. Now the problem is, due to the effect of brush shift, if the brushes are not here, if the brushes are shifted, what is happening in the armature? There is demagnetization, additional demagnetization. So let us consider that additional demagnetization is 2 Webers. Let us consider that additional demagnetization is 2 Webers. So what will be the net flux in the machine? 3 Webers, right? So let us consider additional demagnetization is 2 Webers in the machine due to brush shift. So what is the net flux now? These 2 Webers will oppose automatically 5 Webers, and automatically the net flux is 3. So what happens to the voltage in the machine? So what you have to do now? You cannot eliminate this demagnetizing effect. If you do brush shift, it will come. So if you want to compensate this demagnetizing effect, you have to add some extra turns and produce exactly equal to the demagnetizing effect. Yes or no? Don't produce more or less. If there is 2 Webers demagnetizing flux, add exactly some turns which produce exactly 2 Webers. So you produce 7 Webers out of the pole. In an event of brush shift, if there exists any 2 Webers, it will compensate. And what's the net flux coming out? 5 Webers, and you will get net voltage. Is the point clear? This heading is representing these 2 Webers. Yes or no? Once read the heading, what is that? Demagnetizing ampere turns. What is ampere turns? MMF. What is MMF giving? Flux. What is that flux? Demagnetizing flux. This one. Is the point clear or not? So that demagnetizing flux you are calculating, and that demagnetizing flux should be compensated by all the poles, not one pole. Demagnetizing flux should be compensated by all poles. It should be distributed. That's the reason why you are calculating per pole. So what is the unit of this? Ampere turns per pole, right? So this is ampere turns per pole. I am writing this as simply 2B. Now, you know ampere turns. if you want to derive turns from ampere turns, what you have to do? Divided by amperes. I'm repeating again. There are ampere turns here. If you divide it by amperes, what you will get? Turns. What you are adding on the pole? You are adding turns. What is the ampere means? Already there is field current flowing in them. This is not the process which you are doing after the machine design. This is done before the machine design itself. You will be calculating the press shift, everything, and if 5 turns produces 5 Webers normally, due to press shift, some additional demagnetizing you have to calculate, and while designing itself, you have to extend the number of turns to that value. So let us consider these are NSH extra turns. These turns are some extra turns to compensate demagnetizing effect. So what will be the current flowing in these extra turns? Same current, ISH only. If ISH flows in these turns, all are in series. In this also ISH will flow. So how much flux this should produce? These extra turns, how much flux should produce? 2 Webers. Why 2 Webers? Because demagnetizing flux is 2 Webers. Now, the extra ampere turns should be equal to demagnetizing ampere turns. Yes or no? The extra ampere turns you are placing on the pole should be exactly equal to demagnetizing ampere turns. Let us say there are this many demagnetizing ampere turns per pole. Should be exactly equal to what? NSH extra into ISH. Did you understand this equation or not? You want to produce extra flux to exactly compensate demagnetizing flux. Who is telling you this much amount of demagnetizing flux means ampere turns per pole? Demagnetizing ampere turns per pole is representing these 2 Webers. You are adding extra turns to compensate. So this extra turn should be exactly compensate this one. So this should be equal to this, right? Then what is NSH extra? ATD by P by ISH. So these many terms you have to calculate, and while designing the machine itself you have to extend those many terms. That's why you have calculated these things.
Thank you, sir. छुट्टी सर. छुट्टी.
Or you can take a break. 20 minutes, you know.